streamed. So I'm going to ask our AV member Phoebe to play a brief intro. Welcome to the world-famous Adventurers Club of Los Angeles. My name is Grant McComb, and it is my absolute pleasure to introduce tonight Laura May Abron, a French public astronomer, science communicator, and artist from Paris. She studied art at the University of London and astrophysics at the Paris Observatory, has created and hosted multiple science shows, and currently works at the Griffith Observatory. Her science art has been featured by NASA, New Scientist, and galleries internationally. In her free time, she chases tornadoes, sunspots, auroras, volcanoes, and eclipses. Please give her a warm welcome as she comes on up.
Do we have the slides on? Just a question regarding the slides. Thank you so much for having me, by the way. Privileged to be here amongst this wonderful group of people. Very special to be here today because today, it did not happen, but it will happen tomorrow, hopefully, is the launch of the JUICE mission. I was at a conference about this about 10 years ago with the PI, principal investigator, I believe Michelle Doherty. The JUICE mission is an ESA mission to Jupiter that will investigate the icy moons of Jupiter. So it's going to get there in 2031, so in 8 years. So this is why people in astronomy, we try to live long lives because, you know, it takes a long time to get to places. So there you go. All right, let's see if we can get some slides up. I've got some phenomenal, hopefully, illustrations for you today.
They're up on the sides.
Okay, brilliant. Thank you. If I can have the next slide, please, our introduction slide. All right, fantastic. So, what is an exoplanet? You might be wondering, right? I had someone at the observatory more recently ask me, are there any endoplanets? Endoplanets technically would be planets inside our solar system. So exoplanets are planets outside of our solar system, right? So these are all the planets that we've been finding with this very, very new science. So it's a very interesting time. Now, I do want to tell you also that exoplanets don't have a fixed definition. So you might have heard of something that happened to Pluto. I know people are very sore about this. So Pluto was demoted to dwarf planet. I say upgraded, frankly. It's a very interesting class of objects. But we don't have an official definition of exoplanets, believe it or not. So I think it's kind of interesting what will happen also in the next few years as we refine our detections, whether or not we start having better constraints on what we've got, right? So we've got right now in the catalogs, we have a lot of things that are smaller than the moon, for example. We've got planets also that straddle the line of brown dwarfs. If I can have the next slide, please. All right, so right here, our beautiful Pluto with that little heart on it. So here's an illustration that shows you brown dwarfs. So brown dwarfs are these kind of exotic objects. They are bigger than Jupiter, but they are smaller than stars, and they are fusing deuterium, right? So very interesting objects. We kind of consider the line between very large exoplanets and brown dwarfs to be around 13 masses of Jupiter, right? So 13 times the mass of Jupiter, we've got our beautiful brown dwarfs. So very interesting time for all this. Next slide. All right, so I'm going to tell you a little bit about the brief history, which is actually longer than one might think, even though it's a very fresh field of science. It's a great illustration of, kind of looks like a tornado chaser, actually. Kind of looks like they're reaching for the clouds, which people in astronomy, we all know what that's like. All right, next slide, please. All right, so there we go. We've got this beautiful Herodotus. Sorry if my pronunciation sometimes in English a little different. Let me read you the quote. In fact, hold on. Let me just open the slides for you so that I can read it because the screen is a little small here. So this is just to show you how long we've actually been thinking about this. We have had ideas about exoplanets for quite a while. So this beautiful quote, "Furthermore, there are infinite worlds both like and unlike this world of ours, for the atoms being infinite in number, as was proved already, are borne on far out into space. For these atoms, which are of such nature that a world could be created out of them or made by them, have not been used up either on one world or on a limited number of worlds, nor again on all the worlds which are alike or on those which are different from these, so that there nowhere exists an obstacle to the infinite number of worlds." Now keep in mind this was said about 2,000 years ago, more than 2,000 years ago, right? So people are already thinking about this stuff. Next slide. So next we have the person who is considered the sort of patron saint of exoplanets and of thoughts about exoplanets, Giordano Bruno. And so I use this quote, in fact, specifically because it is so consequential to, again, you know, ideas of cosmic pluralism. You have to think about how long we sort of thought of Earth as really the center of everything, right? The center of our universe. And so, you know, he spoke a little bit about also how, in a way, this isn't totally disconnected from the idea of a god, right? People had religious ideas, and it's not distinct from it to think that there would be other planets. And Giordano Bruno said something incredibly insightful for, again, 1530. In space, there are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. We see only the suns because they are the largest bodies and are luminous, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no worse and no less inhabited than our Earth. The unnumbered worlds in the universe are all similar in form and rank and subject to the same forces and the same laws, right? Absolutely brilliant. If you think about it, our major difficulty with finding exoplanets is that unlike stars, they are non-luminous. So really an incredible thing to have been thinking about. Next slide. All right, next we've got another quote by Sir Isaac Newton. In fact, let's straightforward just to give you an idea that a lot of people were thinking about this. So next slide. All right, and then we get to the really interesting stuff, which is when people started to actually try to do science, right? So we had some early, not quite discoveries, but publications. So both of these very prestigious journals in the sciences. We've got Nature, world famous, and we've got the Royal Astronomical Society in London, the monthly notices, also considered very prestigious to be in there. And so they thought they had found some exoplanets through a method, in fact, I believe through astrometry. And so I'll talk a little bit more about how they did that. These were actually not validated, right? It does happen occasionally that things are published and then are not retracted, but you know, it took a little while. So next slide, please. All right, so finally in 1992, the first exoplanet discovered around a pulsar, right? Very unique type of star. So I do want to say this is technically what's considered a dead solar system. But yeah, we've got a rapidly rotating neutron star, and we found 2 planets around it, and then a third one was found. So on this illustration, you can actually see there are 3. And this was found in, I believe it's in Puerto Rico, Arecibo telescope, which sadly fell apart in recent years and is not going to be used anymore. But pretty incredible to have found this. These planets are still very noteworthy for a couple reasons that I'm going to tell you about. Next slide. All right, and then 51 Peg B, probably the most famous of the planets that we know of, discovered in 1995 by a PhD student, believe it or not. So Didier Queloz, he actually did his PhD in Switzerland, I believe, and Michel Mayor, his supervisor, they were working, I believe, on instrumentation. And so right here on the left is me holding up the telescope on which they found it. I was lucky to do my internship at the OHP, the Observatory of Haute-Provence. I didn't get to use that telescope, but that is the telescope on which 51 Peg B was actually found. And that is a comparison you've got with Jupiter. So it was, many people know of exoplanets as hot Jupiters, right? This was a very, very large planet, a little larger than Jupiter. And again, he won the Nobel for it. I do want to say there's not a lot of people who win a Nobel for what they were doing on their PhD. And they had to do a lot of testing. They redid their observations numerous times because they couldn't really believe that they had actually found an exoplanet, especially because it was a hot Jupiter. And the hot Jupiter means it's very close into its star, right? So think of Jupiter, very far out, hot Jupiter, very close in. And so this upended a lot of people's ideas about planets. And yeah, I think it must have been very, very controversial when this came out. Next slide, please. All right, and right here, something very, very interesting. A discovery that technically you could actually date to 1916. A man called J. Farahi, he actually looked through some old spectra. So spectra, these are kind of like the, I'm not quite sure how to describe them, but that little rainbow image that you get from the prism of light divided. And then we get what are called Fraunhofer lines in them. And this is how we identify a lot of things out there. I actually brought a spectroscope tonight to show you after this. But yeah, spectra is how we find a lot of things in the universe, how we identify rotation, all sorts of things. And so this person actually looked through some very, very old spectra, some archives, and was able to find something that might be an exoplanet. I don't think it's been confirmed yet, but it is the spectra of a white dwarf. So our star will become a white dwarf. And this is the spectra of a polluted white dwarf. So there's debris. So there may be a planet. There may be leftovers from some exoplanets. Hasn't been confirmed yet, but really interesting that we can pour through this data. And I do want to mention that a lot of these plates, so Carnegie, in fact, in Los Angeles, owns a lot of glass plates. And it is very important that we work on preserving them. A lot of these are liable for, floods and fires and things like that. And yeah, I hope we work on preserving all that amazing data. Next slide. All right, so how are we actually finding these, right? Remember, Giordano Bruno, they're non-luminous. Very, very difficult thing to find. Next slide. All right, so I do want to say that we are finding these planets, these exoplanets, in our galaxy. So I believe, in fact, this is probably the field of view of Kepler, that little cone you're seeing. These are somewhat in our neighborhood, right? Very important. We have actually found some planets in other galaxies, potential candidates. I believe it's really just a handful, but we are mostly looking in our galaxy, in our direct neighborhood. Again, non-luminous items, very hard to see. And in fact, the little trail you are seeing towards the center of the Milky Way, those are microlensing exoplanets, which I will tell you more about. Very, very interesting planets, and we tend to find those in the direction of the center of our Milky Way. But yeah, most of them are exoplanets in our galaxy. They're not extragalactic planets. Next slide. All right, so right here we have our detection methods. So there's actually been new methods developed again in the past years. Most of what we're finding, you can see 75%, 3/4 of the planets we're finding are through transit. I'm going to go through all of them in detail to tell you about it. About 20% we get through radial velocity, which is, that is how 51 Peg B was found. We will get some of them through microlensing, which is what you just saw again. I'll talk about it. And then we get just a couple through imaging, right? So you have to keep in mind there are direct methods of finding exoplanets and indirect methods. So most of our methods are indirect. We are actually analyzing the light and the effect that these planets have on their stars and on the system around it, right? Very important. And the direct imaging, it's interesting. We find some interesting things. I will tell you more about it. Transit timing variations. This is mostly to do with pulsars. We are identifying any anomalies in how these pulsars are rotating. And then we've got disk kinematics. That's a new one. Didn't exist a couple years ago, or certainly wasn't really in the ether. We are identifying gaps created in a formation disk, in a protoplanetary disk. We are figuring out if there is a planet carving a path through a disk. So very cool stuff. All right, next slide, please. All right, so right here we've got examples of transit photometry. So most of the discoveries you are hearing about are done through transit. The Kepler is the most famous mission. Now it's TESS, Transiting Exoplanet Survey, I believe. And so what we are doing is we are looking at the light, the flux coming from a star, right? And so we are analyzing these little pinpoints of light, and every now and then there is a slight dimming, right? We experience a little bit of a dip, and so that flux and that little dip is how we know that there's a planet there. And in fact, you can see that there are different shapes here. I don't think we have a V shape on there, but we can also identify atmospheres occasionally by virtue of the shape of that dip, right? Occasionally, if it's V shape, that'll tell you again how sharply the light is diminishing, etc. So transit, really interesting science and fairly fresh, fairly new. Most of that is done exterior to our atmosphere. Again, the Kepler mission did a lot of that. Next slide. Now, a couple of issues with transits. Transit is a great method, but there are a lot of false positives. So right here, you've got, for example, we've got we've got a planet orbiting, but we can have all sorts of things that appear as transit, right? So if we have one of those brown dwarfs that I told you about, or a low mass star passing in front of it, right? That can appear as a transit. Or we can have a blended stellar binary. So again, they're very close together. And there's something else that can also appear as a transit. Next slide. One of my favorite things. Unfortunately, we don't have the animation, but it was to show you the rotation. Sunspots. We are at an amazing time for sunspots. I will not go on about sunspots, or you will be here all night, as some of you know. But yes, sunspots, again, people frequently ask me at the observatory, how long do sunspots last? Sunspots can last several months, believe it or not. Some of them can actually go around their star and just keep going, and they can last quite a while. Some of them will vanish in a day, but they do change shape, but again, they can keep kind of the same amount of, darkness to them. That is a cold region on the sun or on a star. Not all stars have them, but stars with a magnetic field have them. So very important that we figure out more about sunspots to also differentiate them from exoplanets. Next slide. All right, so here is something also important to know about transits. Just because we don't find a planet with the transit method around a star doesn't mean there aren't any. And the reason for that is that we are only seeing planets that are in our line of sight, right? So if you're looking out, you need to basically be looking in a certain direction, and that little tiny amount of the star's width is going to be the angle on which you have your planets aligned. Now, generally, most stable solar systems are relatively planar, right? Most things are on the same plane. But again, if they're tilted a little bit more, so there's quite a lot of stars where we're just never going to find these planets by transit because they're just not aligned to us. They're rotating at a different angle to us. And that's something else that is a bit of a tiny bit of an issue. Next slide. Now, next is radial velocity and astrometry. And so radial velocity, that's how we found 51 Peg B, and I want to tell you a little bit about the concept, also just if you're not familiar with spectra and things like that. So when we have two bodies orbiting, generally they will orbit a common center of mass. Now, people often talk about, again, well, we know that the sun is at the center of our solar system and the Earth orbits it. Actually, the sun is also orbiting us a little bit, right? We get a little bit of a wobble. And so that wobble that we get, it's being tugged on by a planet, right? All these stars are being tugged on by a planet. So on the left, what you're seeing is a pair of, for example, binary stars, right? So these two stars, relatively equal mass, and they are orbiting a common center of mass, the barycenter. And so sometimes we can detect, again, these little movements. On the right, however, you have the example of, for example, a system like either the sun and Jupiter or the Earth and the moon, for example. And so you will see again that that barycenter here is inside the much more massive object. So these wobbles, very important because, next slide, we are detecting basically some shifts in the spectra. So again, I will show you a little later, but that little rainbow will have a little bit of a shift to the red, a little bit of a shift to the blue, and that's how we are detecting these little wobbles. We are detecting literally the planet tugging on there. And there is a little bit of a difference between astrometry and radial velocity in the sense of the direction that we are seeing. So the wobble we are seeing with radial velocity is a movement in longitude towards us, right? Either the star is coming a little bit closer or going a little further away from us. With astrometry, we are not not really detecting that. We are looking at the transverse motion, basically. It's a lot harder to do astrometry. The Gaia mission that's currently out there, I had heard they were supposed to return tens of thousands of planets. I think they are still working on a lot of those catalogs and releasing that, but they are doing astrometry. So very, very interesting, but a little underdeveloped in my opinion, and I think we're just still trying to work on it. Next slide. All right here, one of the most awesome images ever taken, the Smiley Galaxy Cluster. That's how we all feel tonight, right? So right here, you are seeing something that we can do thanks to relativity, special little effects that Einstein predicted that were then tested during an eclipse in 1919. And that is the fact that mass will bend light, right? So oftentimes when we have these images, what you are actually seeing is a galaxy whose light has been bent around a massive object. So oftentimes this allows us to see very, very distant objects in the universe, which we couldn't necessarily access to either because they're hidden behind something or they're just too far. Oftentimes it can create a cross that's called an Einstein Cross. So we've got the object will appear 4 times. And oftentimes in these images, you can look up more of them. You will see the same galaxy imaged in different parts of the image. And so we've decided to use this to find exoplanets. Next slide. So again, it's a little bit of a complicated process, but this is roughly how it works. You've got an observer, and then you've got an object passing in between, for example, a distant star, or cluster, or galaxy, and you will see a little bit of deformation of light as that planet is passing in our field of view. Urge you to look up some videos of it. It's really pretty amazing that we can actually do that. Now, the one thing I will say about gravitational microlensing, we often can't reproduce these events, right? These objects are passing in front, and it's quite difficult to reproduce these events. So it's not our favored method, but it is out there. Next slide. All right, and right here we've got direct imaging. So direct imaging, usually we are identifying things glowing in the infrared, right? It's a little difficult to see non-luminous objects, as Giordano Bruno pointed out. And so right here, you've got an image comparing what you see in the visible of a star, and then what you're seeing if you turn to the infrared, right? And you are seeing a little planet that's near that star. Next to it, we've got the image of a forming disk. I'm trying to remember which one. Let's see. The PDS-70 system, this is a fairly recent image. So you're seeing that little accretion disk, and then you're seeing that planet that's right there that's forming, or it's certainly glowing in the infrared. Direct imaging is difficult to do with many types of planets. Next slide. All right, so this is also just to show you an example of a paper that came out in 2021 on solutions for all the data we have. I went to this fantastic talk recently that was discussing how we're going to start using AI to sort through all this data. We have so much data, and I don't know if it's true of the other sciences as well, but we have all these missions, we have all this data, and we need ways to sort through it. And so they've actually found ways to use deep learning to actually tease out some exoplanets from all of these signals. Keep in mind, we'll get 100,000 signals, for example, to comb through. And so it's very important that we start to maybe automate this. Galaxy Zoo actually started a project recently. Galaxy Zoo is an online sort of public classification system where you can yourself go out and you can go there and look at transits and think, oh yeah, that looks like a planet, or not. So I call it data hoarding amusingly, but we really do have an issue with the amount of data we have in science and in astronomy to comb through. Next slide. All right, so right here, this is just to show you a little bit about instrument biases. So all of these methods have biases to them, right? And this is a big part of the problem, is that we are finding specific planets because of our instruments. We're not just finding anything and everything that's out there. All of our instruments, all of our methods are specifically tailored in such a way that we find very specific things. So you are seeing, in fact, on the left, let me check the slide, I believe, yeah, it's transits on the left, that entire yellow pool of planets, all of those are little planets. And on the right, you are seeing radial velocity. And you can already see, so these are classified by orbital period, so that means how close or far away they are from their star. And you can already see quite a difference, right? So with transits, we're finding all these things that are very close in. And with radial velocity, we're finding things that are a little further out. And then with microlensing, those are the little red dots you're seeing. And so you can see that we are finding things that are a little further away, right? So we have some pretty clear biases. Microlensing, we're going to find things only once, so very difficult to confirm them. Transit photometry, we're finding things that are very close in. Direct imaging, very far out. And I do want to say that all of these work together, right? So when an exoplanet is detected, say through transit, we want to verify that through as many means as possible, because that teaches us so many things about the planet. If we can observe it in different ways, we learn a lot of different parameters. Next slide. This is quite tragic. Disappearing planets, it can happen. This was a very, very big deal when this came out. This is Fomalhaut B on the left. What you are seeing, again, little ring, I believe it's a ring of, in fact, icy debris, if I'm not mistaken. And in the middle, we've got a star that's being hidden by a sunshade or coronagraph so that we can actually see things, right? So that we're not lost in the glare of that star. And people were very excited when many, many years ago, we spotted a planet. I don't know if it was the first found through direct imagery, but it was certainly up there amongst, if not the first, second, or third, and people were very excited about this. However, it was probably not a planet. And those are also some of the issues that we face. So you can see on the right, this is a simulation that shows, I guess it's a little bit of a cleared up image of later observations where we saw that it was dissipating. And so what we actually may have observed was two very small planetesimals that crashed into each other and created a little bit of a cloud of debris. And so that cloud is slowly evaporating. So it's still an interesting thing to identify. This should happen there every roughly 100,000, 200,000 years, these kinds of collisions. So in a way, we are very privileged to have seen this anyway. This teaches us a lot about formation models. But yeah, we're sad that Fomalhaut B no longer a planet. Next slide. All right, so here is our tally, and I can tell you I get so nervous when I make these slides. Back when I was in school, I would make these slides, and I'd keep having to refresh them because they keep refreshing the numbers. And so they do update these numbers very regularly. I also want to tell you that everyone's got different counts. This is the NASA count. NASA doesn't own exoplanets, turns out. European Space Agency, also out there, they had a slightly different count. They were at 5,361 when I checked this morning. But for now, our confirmed exoplanets, 5,322. Pretty amazing if you think about how young the field is. And so we've got a division also into what types of planets we are finding. So we've got a lot of Neptune-like planets. You can see that's the most that we've found. Then we've got gas giants. Then we've got super Earths. So those are planets that are a little bit in between Earth and Neptune in terms of size, mass. Then we've got terrestrial, a little similar to Mars, Mercury, us. And then we've got 5 unknown. So again, all of these generally confirmed through various methods so that we can really confirm them, right? And we've got 9,418 planet candidates right now. So all of these are awaiting confirmation. Some we will unfortunately never be able to confirm, but hopefully many get confirmed. They tend to get confirmed in batches. So yeah, every now and then you look at this counter and then you're like, whoa, an extra 2,000. And amongst these, very importantly, about 4,000 planetary systems, which I will tell you more about. But first, next slide. I want to tell you a little bit about these exoplanets that we are finding. So these are 4 just kind of standard classifications. Gas giants, we spoke about, Jupiter, etc. Neptune-like, Uranus, Neptune. Although I do want to say that even though Neptune and Uranus are often referred to as gas giants, they're closer to ice giants, right? They're a little bit different in composition. And then we've got super Earths. So these are planets, like I said, a little bit more massive. And then we've got terrestrial worlds. So like our inner solar system. Next slide. But these are not fixed categories. Again, new science, just a lot of stuff out there. We've got, this is the most official list you're ever going to get. These are the 15 listed types by I think it's the Universal Astronomical Thesaurus. So we've got mini Neptunes, ocean planets, pulsar planets, super Earths, carbon planets, Catonian planets, free-floating planets, hot Jupiters, hot Neptunes, extrasolar, cold Neptunes, etc. You get the point. Lots and lots of different planets out there, and I wish I could talk for 3 hours and tell you about each and every single one, but that's how it is. Next slide. Of course, our very famous hot Jupiters. This is a lot of what we were finding at the beginning, just like 51 Peg B. So these are very large gaseous planets that we are finding, and they are very close into their stars. And there's a lot of theories about that. There's a lot of debates. Where are they forming? Are they migrating? This is really what people are debating right now. And whereas we used to find quite a lot of them, we are finding a little bit fewer of them now. Next slide. You can also have gas dwarfs, believe it or not. So this is a comparison to scale with, for example, our Earth, and you've got supercritical water. So you've got a core that's a little bit like our Earth. We actually don't have that much water on Earth. I know we think of ourselves as a very watery planet, but you can have much more water on a planet. And so, yeah, gas dwarfs. I don't know if we've officially confirmed any, but they're out there. Next slide. And this is a rather unique body. It's called WASP 12b. So you're seeing all these exotic names like 51 Peg B and WASP 12b. Generally, when you see a little letter on the end of a designation, that generally corresponds to an exoplanet. But there are all sorts of surveys. There is a planet called Coconuts 2b, which is pretty cool. So we've got all sorts of, Qatar, in fact, have their own survey, and they just name their planets Qatar 1, Qatar 2. I think that's pretty great. I think we should do that. So here's a recent find, an exoplanet. Sorry for the pun. So this planet is orbiting quite close to its star, and it is actually being deformed. Now, we do have a limit as to how close a planet can get to its star, right? We've got the Rush limit. Essentially, a body will be torn apart if it gets a little too close to its star. This one is quite close, but it is still able to maintain integrity, but it is being stretched. So it's a very flexible body, very, very interesting, especially for components of geology and other disciplines to study, and hopefully we will learn more about these. Next slide. Now not too heavy on the graphs on this talk, but I do want to show you these graphs because I think it's quite remarkable. This was something I really just kind of blew my mind when I realized this. So right here you've got planetary mass, right? We've got planets organized, exoplanets organized by mass. We usually often use either Earth mass or Jupiter mass to qualify these. And so what you're seeing, that little red bar on the left, that is our upper limit for our planets like Earth, Mars, Venus, Mercury. And then that other bar is basically our lower limit for Uranus, Neptune, our gas giants, etc. So everything that we're finding, most of what we're finding, these super Earths, mini Neptunes, is in between those two categories. And if you think about it, we have 8 planets in our solar system, and we don't have any of those planets. That is what we find most of. So again, raises a lot of questions. Is it biases? Is it just chance? We just don't have one in our solar system. There's quite a lot of theories, but next slide. I wanted to show you the difference between, this is almost the same thing, but by radius. So the maximum radius that you're going to have for an exoplanet is going to be about 2 to 3 times the radius of Jupiter. 2 is usually really the limit. And there's a pretty interesting thing that happens with radius. You can actually have planets that are less massive and have a larger radius. It's a pretty interesting thing where the smaller exoplanets will have basically a larger radius, and as they get bigger, they contract, and we get a slightly smaller radius. These smaller ones that have the very expanded atmospheres and gas envelopes are usually called, hold on, what are they usually? Puffy planets. Puffy planets. We like our strange names in science. In fact, I didn't mention, but in those classifications I showed you, the things that are out there that you will see in the media: party planet, egg planet. I've seen diamond planets. People talk about diamond planets all the time. There are really some pretty wild classifications, which tells you a little bit about how little we know of some of those worlds. You will hear the term Earth-like a lot, and again, disclaimers, not to rain on anyone's parade, but oftentimes we don't necessarily know that they're that similar to Earth, right? So they might be similar in mass, they might be similar in radius, they might be in their habitable zone, but we don't really have all the components to affirm this. So next slide, please. This is just to show you it looks exactly the same. So it's pretty impressive that in the past couple years, it's the same. What we're finding, even though we've expanded our detection methods, we are still finding a lot of the same out there. Next slide. So this is just to show you a little bit about how we identify what these planets are made of. Bear with me again, there's a lot of stuff on that graph, but essentially you can see these lines. We've got the planet radius and the planet mass, and so it's with these two components that we really get to understand what our planets are made of. That's why we want to use, again, complementary methods. So right now we've traced, for example, we've put Earth mass and Mercury next to that line that shows iron and rock, and it makes sense. Earth, mostly rock, a little bit of iron. Mercury, a little more iron. So this is a way we have of identifying those. The little green triangles are planets in our solar system. So you can see we've got the gas giants closer to the hydrogen line, and it's a pretty great relationship that allows us to figure out what planets are made of. Next slide. So right here, we've got a water world. Pretty unique, again, compared to the size of the Earth. Shows you the speculative ideas of how they are composed, what they are made of. Should tell you that we really don't have a lot of water on this planet, so I hope we preserve it. But those are just one of the examples of what we have out there. Next slide, please. So this is a multi-planet system, because yes, we do find many multi-planet systems out there. So this is the only one we know of that has 8 planets, just like us. Sorry, Pluto. Kepler 90. So I do want to say, though, that they are bunched in. So all of these planets are bunched in inside the equivalent to our orbit, right? So 8 planets in the space of our Mercury, Venus, and Earth. One of them was found, in fact, more recently. So originally they found 7. Added another 1. Next slide. TRAPPIST-1, probably the most famous system out there. Another one of these multiples. I believe this one has 7 planets. This one is of particular interest to people because several of those planets are in what is considered the habitable zone. Again, I will tell you more about it, but essentially where we think there could be liquid water on the surface. Doesn't mean that there is, but a hopeful place. And I believe they are around a somewhat smaller star. I'd have to check that. But yeah, this is a very interesting system, and I'm hoping at some point we find a system with more planets. There is one waiting to be confirmed, so keep an eye out for that. That will happen at some point. The 8-planet Kepler 90 was confirmed only about a couple years ago, I think in 2017 or 2018. So these are active discoveries. Next slide. So here's something very interesting, which is the verification by multiplicity. And that means that when we find more than one planet, we are likely going to find more than 2, right? So, in fact, it's to show you the difference between a system that can't really exist, that would have stars orbiting another star. Like I said, we do have binary stars out there. But when you have planets in a configuration, it's a little bit different. It's a lot more stable, and it works. So verification by multiplicity, I don't know if it's used that much anymore, but it was an idea that was floating around in 2014, and it helps us confirm more planets when we already find 1 or 2 in a system. So very important. Next slide. So here we have our exotic systems. So you'll recognize the famous planet Tatooine from Star Wars with its 2 stars. And yes, many of our systems out there actually have several stars. Now, we don't know the exact number of systems out there or of stars that are binaries, but the numbers range from 50% to 85%. Pretty large range, right? It's pretty hard to identify exactly because of complicated mathematics with how you classify things, but it's kind of interesting to know that most systems are a little different to us, and that's again going to be because of how stars are forming. So the way stars are forming, they will often form in clusters also, and so we can get multiple stars forming at the same time, and a lot of binary stars out there. So maybe Tatooine out there. Next slide. And this leads us to very interesting orbital configurations. So right here, we've got 3 different types, the 3 main types of configuration. So you've got the P-type, that stands for planetary type. So this is a planet that's going to be orbiting 2 stars, and that generally works, and that generally remains stable when we have a very large amount of space, right? That means that planet needs to be quite far away from those 2 stars so that we have some stability, and it isn't carried away by one or the other. It's kind of in its little corner. Next, we've got the S-type that you can see, and that stands for satellite. So satellite type is going to be a planet that is in a binary system, or trinary or more. And it's just going to orbit around one of these stars, right? The potential for those to be very unstable, again, we need certain elongation between these stars to have some stability. Binary systems are very interesting from dynamics point of view, the type of orbits you can have. And next we've got the Trojan types. So that is the T-type. So here you've got an example of, again, a binary system with a low mass star and a massive star. And so Trojan stands for a little population of items, asteroids, that are in a resonance with Jupiter. So they orbit pretty close to Jupiter, but along what we call these Lagrange points. Kind of think about them as points of balance, where they're able to stay undisrupted. And so we think there could potentially be planets that function on the same kind of thing, right? Trojan orbits around binaries. Next slide. Now, this is my favorite system. It is the Kepler 64b system. And so it's a really, really incredible system. It is a confirmed system, and it's got 4 stars. This is a quadruple system, so we've got 2 stars orbiting each other in the middle, fairly close together. Then we've got a planet orbiting that central group, and then we've got 2 other stars that are orbiting around that entire system. It's really fascinating, and what's fascinating when we find these is to find out how long can these be stable for, honestly, because you have so much going on and so many gravitational interactions. You are looking at giant N-body problems of all these things, so their stability is a question. Next slide. So this is showing you something kind of unique also. This is a planet, a confirmed planet that we often call the Jovian Comet. You might notice that that orbit is very elongated. Now, eccentricity is a parameter that we use in astrophysics to qualify how circular an orbit is. If you come to the Griffith Observatory, we give a local noon talk, and we tell you a little bit about how eccentricity changes when noon actually is, when our sun is the highest in the sky. So there is a population of objects that have very, very elongated orbits. We call these comets, right? That's why they come and visit us, and then they're gone for thousands of years and come back. Halley's Comet, I believe it's either 67 or 76 years that it orbits. Comes back and visit us. So when you have a lot of eccentricity in your orbit, very elongated orbit, and a little bit difficult for stability, and we have yet found quite a few planets that have these very, very long orbits. Ours are fairly circular and stable. Next slide, please. All right, so this is a very unique system as well. This is called the Upsilon Andromeda system, and it is compared here to our inner solar system. So if you look at it again from this polar view, looks pretty okay. We've got a star in the middle, and then we've got 3 planets, one quite close in, one on a pretty large orbit, and another one right in the middle. But if you look at it from the side, then it gets really interesting, right? So you'll notice the planarity, right? So as we think of solar systems, and they tend to form in this disk, we will generally have every planet on a planar orbit, right? Most of our planets on the same plane. And here's something interesting about our solar system. We do have, in fact, our little Pluto. Pluto tilted its orbit is tilted at about 17 degrees to the plane of our solar system. Another reason why it's kind of an oddity out there. And this is something that we do see, and it's something we particularly see with dwarf planets. In fact, a lot of them have these orbits that are really not planar with our solar system. There's something quite interesting that can happen when we get all these very eccentric or non-planar orbits, which is that you can have something called the Lidov-Kodzai mechanism. And that essentially implies that you will have an exchange of planarity and eccentricity. So if you have a companion star that is orbiting around this system, it can sometimes basically do a trade of eccentricity versus the planarity. Affects also obliquity or tilt of our planets. So there's a lot of very interesting interactions happening out there. And obviously these systems are hard to find with transit because, again, you want everything to be in that same line of sight. Next slide. All right, so here is an example of an orbital interaction that happens. There are quite a few out there that have been modelized. So again, you've got here this system, looks a little bit like our solar system. You've got some gas giants, 3 rocky planets, and it goes unstable. Maybe one of the orbits is elliptical, and it just throws everything out of whack. And then one planet gets ejected, and then it can get recaptured by the binary star of that entire system, right? So we can have trades, and orbits can get pretty unstable even in very small amounts of times, hundreds of years. Don't worry, not going to happen to us. We're in a pretty stable system, but these are things that are happening out there, very, very interesting dynamical interactions. Next slide, please. Our favorite, I dedicate these to the Adventurers Club because these are the true adventurous planets out there. You might know that the term planet comes from wanderers, right? Ancient Greeks, they were looking at the sky and they saw some objects that were moving a little bit differently to our stars, a little bit faster. They were wandering, right? These were our planets that they were seeing. And so we gave the name to our planets, meaning wanderers. And so there are some planets out there that are called rogue planets, orphan planets sometimes, or free-floating planets, FFPs, and we estimate that the large majority of exoplanets that might exist out in the universe are actually of this type. These are planets that are not attached to any star. So how do they form? Where do they go? Where do they come from? When you have the collapse of a molecular cloud, start forming a lot of stars, a lot of that material, it can be up to 90% of the material in that molecular cloud is unused and might go into forming some of these rogue planets, right? Some of them might get captured by some stars and become part of a system. Some of them will wander the galaxy. And we have detected, I believe we have about 4 candidates nowadays. They are very hard to find because, again, not attached to a star. Star clusters, good place to look for them. And they only emit light in the infrared. Again, we need a star to compare it to. Occasionally, they will retain some heat from their formation, and that is a way that we might find them. We'd usually find them with microlensing because they're randomly passing there, so we will often not see those again. Really interesting population that I hope we find out more of. Next slide. Now, here is some examples of extremes that we have out there. So as much as we have this very ordered, beautiful solar system that we live in, things are actually pretty close together in our system. So this is showing you an example. We've got the scale on the bottom right. So AU means astronomical unit. That is the distance between the sun and our Earth. That is 1 astronomical unit, about 150 million kilometers. And so here you can see how far apart these 2 objects are. So TYC, that is a star. 2 mass, that is potentially its planet. Might be a brown dwarf, but it is attached to it. And it is at a separation of, if I can have the next slide. So here is the exact separation in comparison to the orbit of Pluto. You can see how tiny it is. So this planet is 230 times further away from its star than Neptune is from the sun, and it is 6,900 astronomical units further, right? So then Earth is from our sun, so a pretty remarkable system, and we are finding some of these, but that one is the record holder. So pretty impressive. There's another one that might be confirmed that's even further out. Next slide, please. All right, so right here we've got our original discovery, the Pulsar planet, and believe it or not, it's still amongst the least massive we have found. Would probably be dwarf planets if they were around our solar system, but it's still the 3rd least massive. And this helps that we detected it around a pulsar. Detections that we make around pulsars are very, very, very precise. We get great precision from these detections, and so we're able to detect these very low mass events and planets. Next slide, please. So right here, I've got a few other extremes for you. So most massive, Like I told you, brown dwarfs. So our limit is at 13 times the mass of Jupiter. That is our brown dwarf limit. There are a lot of things in the catalogs that either straddle that limit or go way beyond it, and we wish we had more information on them. But yeah, your most massive planet possibly in existence is going to be 13 masses of Jupiter. Next, hottest, 7,000 kelvins, right? That's about 6,000, closer to 7,000 degrees Celsius, so very, very warm on this planet. Coldest, 31 Kelvin, minus 242 degrees Celsius. Oldest planet, this one is very surprising. We have found a planet that is 12.7 billion years old. In fact, it was nicknamed Methuselah, and it was found quite a while ago, and it was dated thanks to the age of the star cluster that it's in, a very old star cluster, but we may have found a planet that is older. Now, you might notice that goes beyond the age of our actual universe, 14.9 billion years old. But that has to do with the error margin. We may have found something a little bit older. Hasn't been confirmed yet, but it's an interesting object. Next, we've got the longest orbital period. So our orbital period, for us, 365 days to go around our sun. For some planets, the furthest, famous coconuts 2b, 1,100,000 years. That is how far away it is. It is a contender also with 2MASS, that planet I showed you a little bit earlier, and very, very, very far away. Now, the shortest orbital period is 49 minutes. That is a planet that is taking 49 minutes to travel around its star. Again, remarkable because there are limits on this, on how close you can get to your planet before you get torn apart. Now, the most eccentric orbit, close to Halley's Comet. Not physically close, but the almost same eccentricity. So again, how elliptical that orbit is, 0.97. We measure this from 0 to 1, very, very elliptical orbit, but without the long period, right? So Halley's Comet takes 76 years to come back to see us. Was last around in 1986. This planet takes about 591 days to complete that little elliptical orbit. Next, we've got our largest orbit, Coconuts 2b, as mentioned. So this one is 7,500 astronomical units away from its star. Enormous distance. Next, we've got the planet with the hottest star, right? So 57,000 Kelvin. For comparison, our sun, 5,772. So much, much hotter. And then the planet with the coolest star is 2,000, around a star that is 2,566, so about half of the temperature of ours. So these stars are going to need to be a little bit closer in, and it is in that TRAPPIST-1 system. So, next slide. Next, we've got our stellar types. I wanted to talk about this at length, but I will not, because that could make a whole other presentation. You should know that most of what we've been finding tends to be around smaller stars. So here we've got our classification that we often use in astronomy, and you can see the hotter, bigger stars, well, hotter mostly, are those blue stars on that top left corner, and then we've got the red giants, the final phase, or one of the phases that awaits our sun at some point in a long time. And so along that middle line, you've got our sun, right? Our sun is a G-type star, and then you've got F and K that are a little similar, and then you've got the M's, which are these red dwarfs. Most of the planets we are finding are going to be around these stars. There's a couple of reasons for that. We wish that we could sample every single star and decide, well, there are more planets around this type of star, or more planet around this type of star, but we can't. And part of the reason for that is that they have very fast rotation when you're up in those very energetic blue stars. And that creates something in our spectra. Oftentimes, it can broaden the line, it can make the lines, in fact, disappear in the spectra, which is part of how we find them. For the very, very dim stars, it's also very difficult. We will get very broad lines. So all of this is something that hopefully at some point we can resolve, because we'd like to find out what kind of stars are more likely to host planets, but still trying to figure it out. Next slide. So here we have a concept you've, I'm sure, heard about called habitable zones, often talked about also as the Goldilocks zone, where it's just right for liquid water on the surface. Now, I personally am not a big fan of this concept for a variety of reasons. We have quite a few ideas on, do some of these planets have water on their surface? And in what state would that make them livable? We also have ideas about, for example, one of Saturn's moons, quite far out in our solar system, Titan, a very interesting place that we landed on many, many years ago. You can look up the video of the Cassini-Huygens probe descending on its surface. We think it may have had a greenhouse effect in the past. Mars also may have had oceans in the past. Venus could have had oceans in the past. And then we've got the ideas of moons, right? Living on the moons of, for example, a gas giant as depicted in some films. Here's something else. The planets that you see on the very bottom, the stars that you see on the very bottom, these are generally these red dwarfs, you'll notice that their habitable zone is going to be much, much closer in, right? They are much dimmer. Some studies came out, very interesting, about photosynthesis. This is for the biologists. Someone here hopefully can tell us about that more. But we are not certain that photosynthesis, as we see it on Earth happen, could be possible on some of those planets orbiting those stars. Are those stars too dim? Those little small stars also have fairly active surfaces, fairly active processes on their surfaces, so they would bask those planets in radiation. Not so great for life. So habitable zone, debatable concept. That dark green line corresponds to a more optimistic scenario. The thinner one is a more conservative estimate. It's a good starting point, but there are a lot of things that revolve around a planet being habitable, and we need to know more. All right, next slide. Very exciting topic. I have brought you a very special book, Good Night, Exomoon. Believe it or not, that was actually published. This is the only exomoon that you're going to see because we do not have any exomoons yet. We have not found any. They should be out there, right? In our solar system. I checked, in fact, the figure last night because this gets updated all the time. I believe we have around 226 moons in our solar system, and that's not counting moons that are around maybe asteroids, objects like those. We've got even more of those. I think the tally goes to about 460 when you tally those, but we've got 226 traditional moons around Jupiter, Saturn, etc. So how do we find exomoons, right? We're finding these tiny little dim planets, and we're trying to find moons that are even dimmer and even smaller. This is a very novel idea that I discovered a couple of years ago in a paper. I don't know if it's been used, but you might be aware that Jupiter has a moon called Io. Io is a very volcanically active world. It's one of the few very volcanically active worlds in the solar system. So Io is actually emitting quite a lot of material, and it is creating around Jupiter a torus of sulfur ions, right? So this is an image to show you what it looks like. Again, you've got certain wavelengths. You are not seeing this in the visible. And in fact, when you look at Saturn's rings, it's a little bit different, but Saturn has a moon called Enceladus, and it is creating what we call the E ring around Saturn. Much harder to see it, but it is a very diffuse ring. Enceladus has some very active processes on its surface. It's ejecting, it's got geysers of ice. So this is one idea, would be detecting this. Essentially, detecting that ion torus is one way. We have a variety of ways. There was a mission called the Hunt for Exomoons with Kepler. I don't think it turned out anything. Every couple of years, someone finds something and wants to confirm it, but we don't have any confirmed exomoons yet. Next slide, please. So this is a very brand new image, again, cutting edge science. This is an image from the James Webb Space Telescope, and you are seeing a planet visible, again, in 4 different wavelengths shot by the James Webb. Now, just to remind you, the James Webb Space Telescope, anyone who says Hubble no longer interesting, no, they do different things, right? James Webb is shooting mostly in the infrared and in a band of infrared that we don't really have anything else for out there, different band of infrared than Hubble. And so we are able to see quite a lot about exoplanets. James Webb is doing quite a lot of stuff to do with also atmospheres. So really our first big mission out there that can look at atmospheres. So the strange shapes you are seeing You've got the star there on the image, and then you've got these little weird shapes that is to do with the hexagonal mirrors. I'm sure you've seen the images of the James Webb mirrors. So, next slide. Looking into the future. So this is the Nancy Grace Roman telescope. On the left, we have Nancy Grace Roman. She is considered to be the mother of the Hubble Space Telescope. She was part of the people that made it happen, one of the major architects of it. And so we will be launching that one in 2027. Also a very interesting mission. It's got a very wide field of view, and it is going to work on, let me see, it's going to be actually directly imaging. It's going to be doing some gravitational lensing, and it's going to be directly imaging some Earth-like exoplanets. It's got a pretty big mirror, and we're looking forward to it. So yeah, next slide. And here are all the missions that we have out there, upcoming, former missions. I know that here we hear a lot about all these amazing NASA missions. I do want to mention that the James Webb, by the way, is equal parts. It is also European Space Agency. And there are some missions that we don't talk about as much. Corot. Corot is one of the European Space Agency missions, and it detected a lot of planets. We've got, of course, Hubble, Spitzer, Kepler. Kepler was our main thing to find all those transits. And then we've got Gaia that I mentioned. This is an astrometry mission. It's doing very, very important work. It's cataloging all of our stars, creating giant star catalogs so we can have very, very precise measurements. TESS, of course, current mission out there, transiting exoplanets. And then we've got Cheops. Cheops is a mainly ESA mission, and it is characterizing all of these exoplanets. So once we've got a target, we send Cheops on them and we get more information. The James Webb, Plato will be launching in a couple years, Roman, Ariel, and more. Next slide. These are just to show you some of the ideas that are also hanging in the balance. One of these two will probably get approved, I hope. This is Habex. That's not going to launch until 2035. And then we've got Louvoir. You can see it's got this absolutely gigantic mirror. So again, that will do a lot more than what we have out here. We on a race for always having bigger telescopes. That is a problem for anyone who actually owns telescope. I think everyone's familiar with that problem. So next slide, please. And then we have this wonderful idea, the Solar Gravity Lens Telescope. So remember what I was telling you about micro-lensing, right? We are using mass to bend light. So we have some ideas to do this using the sun. Now, we could get incredible definition of exoplanets doing that. Here's one of the problems with doing this. This is feasible, and this could be done, and maybe people in 100 years will be using this, but we have to put this telescope very far out. So this telescope has to go to about 500 to 800 astronomical units. Now again, 1 astronomical unit is the distance between our sun and the Earth. Keep in mind, Neptune, our furthest planet, 30 astronomical units away. So we are putting these objects 800 astronomical units away, so very, very far. To give you also a point of reference, in fact, the Voyager mission, Voyager 1, furthest object, furthest probe we've sent, currently it's at about 160 astronomical units from us. So this should tell you how incredibly far we would have to send this. Not currently feasible, but it's a really amazing idea, and a lot of people in science are talking about this. And we would actually get a resolution with something like this of about 10 square kilometer for objects about 100 light years away. So really, really neat idea. Next slide. So here's a really cool idea also. It is called specular reflection. And so we would actually be trying to identify the reflection from alien cities. Again, this is a little sci-fi, but we also know that, for example, lakes on surfaces, we have seen this with, I think, methane lakes on Titans. We are seeing a little bit of reflection of light. So it's an interesting idea. We might not just use it for alien cities. I don't know that we're going to find a lot of those, but we would be using also polarized light to figure out differences between reflection coming from lakes, reflection coming from perhaps cities, technology, things like that. Next slide. This is another wild idea out there. So here we've got some cataclysmic variables. These are types of stars. And we think that if a third body was orbiting this, so a planet, it would actually influence the mass transfer that you are seeing between these two stars. This happens with some very close-in binaries at times, and so it would affect the brightness of the entire system. So truly, the amount of ideas that are out there that are just incredible. This is really something that, you are really seeing the cutting edge and really just the start of this entire science. Next slide, please. All right, so this is just to give you a little bit of a conclusion of everything we have on here. So really what I was just talking about, the ingenuity of detection methods. Didier Queloz, who found 51 Peg-B, was an instrumentation person, as I mentioned, and really instrumentation is a big part of our science of astronomy and astrophysics. The things we are achieving now, we have left Earth, are remarkable. We do have a lot of telescopes down on Earth that are also working on exoplanets. It's not just done outside of our atmosphere, but we are getting smarter and brighter, and it is a testament to, I think, human ingenuity to have all these amazing detection methods. We find both surprising and expected. We are finding very stable systems out there that tend to a level of organization. So most of our multi-systems, they're very compact, they're very ordered, and we pretty much now think this might be the favored outcome of formation models, at least the ones we are finding that are stable, right? Anything that's gonna have wild eccentricities, planets that are orbiting out of the plane, we're not really sure how long the stability of those systems is. So next, the more planets, the more balance the system exhibits. Again, is it because those systems formed with a lot of planets? Is it that regularized it? It's rather interesting that we live in a very stable system with 8 planets, and that is roughly what we are seeing out there. We are generally finding that planets around between, well, these are radiuses of Earth, but we are not finding those in our solar system. So that's what I was mentioning to you, the great dearth of these super Earths, mini Neptune. Why do we not have them here? We have some ideas, potentially to do with Jupiter's migration. We think Jupiter may have migrated inwards to the solar system. It's a theory called the Grand Tack model. And so the Grand Tack posits Jupiter migrated inwards, disrupted potentially the formation of Mars. Mars could have been a super Earth, left us with this mini Mars and this asteroid belt. At one point, Jupiter was actually as close to 1.5 astronomical units from our star, so it got to be very close in if this theory is correct. So next we have everything is moving and interacting, and this is something we talk a lot about at the observatory, especially when we do local noon. Really, you have to think of everything out there as a grand n-body problem. We talk a lot about 3-body problems, how difficult it is to predict over a long period of time, the movements, and to predict where things are going to be, right? In systems that have basically more than 2 objects. That is why we have limits on how far we can actually make eclipse catalogs, for example, right? Our precision is going to be affected by this. So everything in the universe is moving, even stars, as you've learned around their barycenter. Next, exoplanetary atmospheres, and in fact, I should have mentioned geology as well. This is going to be very, very important. Like I said, James Webb is working on that, and that's going to be, I think, really, we've reached quite a good understanding of the kind of planets, exoplanets we have out there. Now we need to figure out their atmospheres. We need to figure out if they've got magnetic fields. We need to figure out their geology. I found out recently about eggshell planets. Those are planets that have a lack of tectonic plates. They might be quite fragile, and they've been called eggshell planets. Rather nice names. Next, the number of exoplanets out there, and I want to tell you that number is astronomical. I'm sorry, please laugh. Anyway, so you have to think we've got 200 to 400 billion stars in our galaxies, and we've got about 10 trillion planets without accounting for the free floating planets, right? So 10 to 100,000 planets per stars is a potential estimate, again, because a lot of them are forming outside of systems. So I hope that gives you a lot of inspiration as to, every sci-fi you're seeing, just everything that could exist. I wrote out that number for you because we all like to see those gigantic numbers. I will not attempt to pronounce it, but that is the potential number of orbiting planets in our observable universe. Next slide, please. And I will end on this wonderful quote. Nature is amazingly good at making planets, and she puts them wherever the hell she wants. This was said in an interview that I found a long time ago by a man called Nick Cohen of McGill University. And it is quite accurate. We really just find these things absolutely everywhere. And to have gone to this realization, if you think about the debates that we had 100 years ago, whether we live in a galaxy, whether we live in a nebula, or there are other galaxies out there, and now we're actually finding planets around other stars. Truly remarkable. I hope that this really paints a picture of the kind of adventures that we may have. I know not right now, but potentially in thousands of years, we may be able to travel to these places. That is the main issue right now, is traveling to these places. So there you go. Thank you very much for having me. Thank you.
Ladies and gentlemen,
we're going to take a second. We're going to take a second here and ask a few questions. I'm going to start one off. Lance Miller, 1222 with the Adventures Club. You mentioned sunspots. I don't want you to go real deep in it, but
Oh, but I will.
Okay. Correlation between the sunspots and the shifting climate and weather on the planet. Is there a direct tie to that?
That's a great question. There is none. We are currently in a very, very active cycle. Maybe it'll be the most active cycle of our lifetimes. We actually are about to reach solar maximum, so that's when we are going to have the most number of sunspots for this 11-year cycle. That will happen probably rather sooner than we had planned. We had planned for 2025, and it's actually happening potentially this year or the next. Does not have correlation with climate change. In fact, the difference in output that we get from the sun is actually quite stable despite these sunspots, despite this difference in activity. And we've actually been monitoring this because it is a great question. And I think it's perfectly fair for people to wonder, well, is the sun just getting hotter? Is it the sunspots? Is it mechanisms on the sun? And we've been monitoring this now for about 50 to 70 years on our planet, the amount of light, the amount of heat, everything that we're receiving from the sun. There are missions dedicated to this. And we know for certainty now it is not the sun, it is definitely us. So sunspots do have some influence on our technology. That is the biggest thing right now. But yeah, no connection to climate change, surprisingly. But yeah, our star, quite stable.
Hi, Ray Castillo, member 1233. So you mentioned earlier in the presentation that certain exoplanets can be warped and misshapen by their stars.
Yeah.
My question is, how come something like Mercury that rotates so close to our sun and is composed of primarily metal doesn't see that kind of misshape or deformation from our sun?
Yeah, so Mercury is an interesting place, and it actually has the highest eccentricity. If you remember what I was telling you about how elliptical that orbit is. So Mercury is actually highest eccentricity in our solar system. It's 0.2 on a scale of 0 to 1, so that's quite a lot. I think Earth is 0.0 something. Mercury also has some gravitational anomalies on it, zones of interest, interesting features to it, but it is not close enough. It is not past that limit where it would break apart. But we do have some ideas that in a very long time, there could be some changes in all these orbits of our inner planets, and we could have some collisions. We could have some collisions between Venus and the Earth, between Venus and Mercury. On the long term, again, we are looking at three-body, n-body problems. And yeah, so Mercury is far enough away, and I know it seems like it's very close and it is getting baked, but it is far enough away. And when you compare it to some of these systems like that egg-shaped ones, pretty much we actually have a peak of exoplanets that we find around 3-day orbits, right? So we are finding a lot of planets, small planets that are orbiting around their star with 3 days, 3-day orbital periods. And the rocky ones will also survive a little better when they're closer into their star than the gas ones. So they have a better chance of surviving. And yeah, Mercury actually at a pretty safe distance from the sun.
David McAlexander, 1199. I think I heard you say that we, off James Webb, we may get not just atmospheric data, but geology data. Because I understand looking, the sun's light going through the atmosphere, we can
Yeah.
get spectral lines off the atmosphere. How can we get geology data?
So I mentioned in the end that I hoped that one day we can get geology data, but we will not get geological data from James Webb. We are getting atmospheric data. Occasionally that can inform us, of course, as to the geology of a place. And certainly many studies will be done stemming from that atmospheric science as to what kind of processes on the planet, what kind of geological processes are going to then feed into these kind of atmospheric processes. But no, only atmospheric data.
I took a quick shot of the instrument biases slide, and I found it was curious that for the transit data, or I guess exoplanets were found via the transit method, there was a large cluster of discoveries around one Earth mass, and similarly, pretty close to like the Earth days transit amount, and it was just this kind of large glob. I mean, you know, it sort of had a smaller glob that was a little bit more mass. I was just wondering, is that an artifact of bias, or is there something that maybe can be indicative of that's the kind of thing you can see generally?
Yeah. So originally we found a lot of hot Jupiters, you know, when we were first discovering these, because they're so massive and they were so close to their star, we were finding a lot of these. And then, as you rightly pointed out, then we're finding things that are a little closer to Earth, right? Someone in fact asked me, like, are you guys looking specifically around there? No, we can't. We wish. But no, there are definitely biases. And again, these are pictures that we're building. We only have 5,000 planets right now. So all of these, it's hard to know. Is it chance? Is it a bias? In our own solar system, like I said, we don't have these sub-Neptunes, mini Earths, super Earths, even though we're finding them absolutely everywhere. We think Planet 9, for example, actually that one could be, if we find it. Research is ongoing at Caltech to try and find a 9th planet that would be very far out, could be a super Earth. But it's a great point. And, you know, these biases, they will find things that are close in. So that is, and they will find things within certain mass ranges. And also we're looking at certain types of stars. Kepler, a lot of the transits are from Kepler and TESS. They're looking around specific types of stars, and you will also have constraints on the amount of mass that you have in those systems for the original formation.
Well, I'm Jean-Luc Picard, the captain of Space Enterprise. And
Our next adventure.
I'm Adventurers Club number 12,833. Listen, this is the most amazing lecture.
Thank you. I appreciate that.
And I'm from Serbia, and we are from Croatia, Serbia. We are the most knowledgeable now. We know more about this than anybody else.
Listen.
Anyway, you are excellent lecturer.
Thank you. I appreciate that.
I love your English language. I will never speak like you English. This is such a beautiful pronunciation. I usually fall asleep, but this you can.
I have an American mother,
so many
I do
questions.
cheat.
Like, I don't know anything. I'm country doctor and stuff. So, is there a God? Is there an end to this galaxy? Is that so small?
I don't know that I'm qualified to answer that.
That there is somewhere double people, all of us like this, you know, somewhere else. Is there any other creatures like human beings or not? You think, you believe?
It's a great, you know, the question of life in the universe is why we do all of this. There was a talk here a couple months ago that I attended. He was one of the people who founded the Planetary Society, and we were talking about Mars sample returns, and you know, I asked him, I was like, what's really what we're hoping to find here? And he was like, oh, life. That's part of why we're doing, I think, everything. Of course, curiosity. Adventurers Club is here for curiosity, right? As we all are. But we want to know if we're alone out there. And I think we are, in some way, answering, or Muslim or Christian, theological questions in some capacity. And there's cosmology, especially cosmologists who work on the very large scales of things in the universe. Oh, you know, I think the line is straddled between philosophy and cosmology and the kind of things you're looking at, these structures. Is the universe infinite? Are we living in a bubble universe? And is there life? I make this bet, and we can come back to this YouTube, if YouTube still exists in, like, I don't know, let's say 30, 40 years, that we may find in our solar system simple bacterial life. I don't know that we'll find complex life. We could, maybe. JUICE, that I mentioned, launching tomorrow morning, hopefully. From French Guiana. It's going to be identifying a lot of things about Jupiter's moons. Very, very promising place. I would be surprised if we don't find very simple bacterial life in our solar system, depending on how much money we put in those missions, in the next, 50 years. And if we find it on Mars, it's great, but it's actually not that interesting because Mars, I mean, it's interesting, but there's a lot of cross-contamination between Mars and us of objects, of rocks, etc. So things can transfer pretty easily, but if we find it on Jupiter, a lot harder to get there.
My last point, like you said something in the beginning, like, oh, this is impossible, something. No, we have Elon Musk. That guy is now better than whole NASA. And
Well,
he's building that big shit. Maybe you should marry him or something like that, two of you.
well, I wait for his marriage proposal on Twitter. Listen, now I do want to say though that NASA, everything that Elon Musk is doing, as great as it is with SpaceX, is not possible without all the people who worked at NASA, European Space Agency, et cetera, and who really, the Apollo programs, we have Artemis, we just had the selection of the crew for Artemis 2. None of what SpaceX is doing is possible without all the work of NASA. And terraforming Mars, though, oof, that's, I don't know that anyone's got the money or the time for that.
Yeah, we're going to take one more question here, okay?
Appreciate it.
Hi, Laura May.
Hello.
I was wondering, you showed a slide that said there's about 10,000 planets that are candidates for being confirmed.
Yeah.
What is the limitation to confirming those? Access to instrumentation? Is that the main
So
issue?
there are several issues. The gold standard for confirming things, especially when you're looking at transits, is going to be length of time, right? The further away your planet is from its star, the longer it's going to take to come back around and for us to detect it a second or third time. And that's really, we don't always, in fact, I don't know what the observation period they had on Kepler was. How long are they looking? They're looking at a pretty wide field of view, but sometimes we might not reproduce the transit because that object passed and then it's on a super, super long orbit and it doesn't come back. Micro lensing, those things, we're not going to reproduce them. The free floating planets, basically impossible to see them a second time. So there's a lot of stuff that's going to sit in the unconfirmed. And again, that number is, I think, teased out from a lot of noise that can be in the signal and things that really aren't going to be planets. But yeah, it's length of time really for some of these things, you have to observe these transits several times. You have to have time on telescopes. Please give us more money, people.
Laura May, thank you very much for an
Thank you.
incredible presentation here at the Adventures Club.
Thank you so much.
All right, everybody, stay.